Okay, so let's continue. So last time we derived this expression for this dielectric functions epsilon q omega by this Dyson type equation, and we need to compute this epsilon, okay, from this RPA method, and we will see later that we could use the Green's function method to compute this pi star, which is the single bubble diagram, and then we could plug in that single bubble into this Dyson type of summation and to get this epsilon. So in fact, this epsilon in this electrodynamics represents the effective interactions. For example, the Coulomb interaction between two charged particles or two charged impurities which differ by a distance, capital R1 minus capital R2. And this effective potential or interaction strength between these two charged particles could be written in terms of the integral or the Fourier integral. Inside the integrand, you have this U0, which is a bare, say, Coulomb potential. But you need to divide this U0 by this epsilon, which is precisely what it stands for as a dielectric function. Okay, so when U0 is divided by this epsilon, this whole quantity is actually an effective potential, okay, or effective Coulomb, and we could perform the Fourier transformation to transform this U effective back to the real space. As a result, this V effective will behave differently from this bare Coulomb interactions. So-called screening of a Coulomb interactions comes exactly from this type of physics. Okay, so later we will see that this epsilon of q and omega indeed serve as a mechanism for, say, reducing this interaction strength in a many-body system, because there are many charged particles in between this E1 and E2, or Z1 and Z2, so that there are many cancellations, and also there are many, say, electron hole pair productions could be generated that could lead to some cancellations of this Coulomb potential between the bare charged particles. Good, so let's do it, but we need to actually link this epsilon to a well-known correlation function, or the Green's function that we already defined, namely the density-density correlation function. Okay, so the epsilon is exactly take this density-density correlation function, and the form of density-density correlation function, you could see this kind of a definition or derivation right here, that suppose I defined some kind of a small density variation, which is the deviation of your number density from the mean value n0, and we call this n tilde. Then we can define this density-density correlation function, which is just the delta n prime correlated, right? And at finite temperature, this is the formal definition of this so-called density-density correlation function. And you take the retarded real-time response function coming from this, say, italic capital D as a imaginary time correlation function of the density-density, and this capital D retarded Green's function is given by this expression where you have this commutator between n RT and n tilde RT and n tilde R prime T prime. Okay, so this follows our earlier definition of this retarded real-time Green's function. And you need to multiply this by capital theta, which guarantee this causality. And you take the trace of this quantity and include this thermal factor. So we'll see in just a moment that this capital D here is precisely this h bar times pi. Okay, where pi is, remember, is our renormalized bubble. Okay, so we'll see that just a moment. What is polarization? Okay, and remember this polarization pi is given by pi star divided by 1 minus u0 and pi star. And pi star is nothing but this particle hole bubble. Okay, so I think to go through this derivation, we need, again, go back to our earlier note on this linear response theory. Okay, so suppose you have some charged particles and the density of that charged particle could fluctuate, okay, from their mean values. And if you perturb this charge system by some external potential, okay, and then you could really induce this some additional charged particle or deviation of this electrical potential. So let's just look at this link between the screening and this density-density correlation function. Suppose we applied some external potential like this, a phi which coupled to the density of the charged particle. Okay, so this is just energy associated with this external potential coupled to this charge density. And we have some induced density times this potential, bare potential 0, which is induced potential, delta phi. Okay, so suppose there's some charge distributions, then we have some test charge Q, and we apply some external potential, and then the whole system shows some density fluctuations like this, and there will be some induced charge density. And also there's a induced potential, delta phi, associated with this induced charge density. Okay, so you could formulate this in this following way. So U0 times this delta and Q omega is your induced potential. And this induced potential up to the linear order in the external field, or phi, is given by the linear response function. Okay, so this is linear response. Okay, so I think in the previous semester we discussed the Thomas-Fermi screening mechanism in the semi-classical treatment, and we discussed this physics. So once we have this external potential which coupled to this charge density, then this test charge Q will actually induce some variations of charge density, and also there is an induced potential because of this induced charge fluctuations. Okay, so but this kind of a small deviations of a charge density variation is actually proportional to this density-density correlation function on the right-hand side times this your applied external field. And we don't go back to this derivation, but you can go back to your earlier note on the linear response theory. So when you really compute this delta phi here, you will end up getting this correlation function, capital D of R, and this is precisely this, say, retarded density-density correlation function right there. So, and we could just define this as called the charge susceptibility, chi q omega times this phi omega. With this charge susceptibility is 1 over epsilon minus 1, which is precisely U0 of pi. And this pi is fully double shaded, fully dressed electron hole bubble. Okay, so this pi star is just a bare electron hole bubble, but this fully shaded electron hole bubble is actually the sum of all such single bubble diagrams, and that is the relation between this density correlation function and the dielectric function epsilon. So we call this capital D the density-density correlation function. Or sometimes density correlator. Okay, so there's a remark here when we calculate this density-density correlation function like this. In principle, we have this disconnected diagram, like I drew here, that there are separate two bubbles, single bubbles that are multiplied together. and each bubble represents this Green's functions. It's a loop of this electron propagator. But we know very well that this disconnected diagram will be cancelled exactly by the other diagrams in the denominator. So we only take into account this connected diagram. Okay? So we throw away this disconnected diagram. Okay? And this is the reason why we define this deviation of this charge density from their mean value, because their mean value represents such kind of disconnected diagrams, which we don't care, and we only care about their deviations. Okay? Okay, so anyway, so this is the link between this epsilon and the density correlator. Okay? So they're related by this equation right here. Okay, and also this relation right there. Okay, so let's take a short break. When we come back, let me just write down the formal definition of this 1 over epsilon minus 1 in terms of this density correlator. Okay, so let's define formally this 1 over epsilon, this inverse of the dielectric function, okay, which is given by this one, okay, which is imaginary time Fourier transform of this density correlator, evaluated at imaginary time 0 and tau, and the momentum is actually q and minus q here. Okay, so if you perform such an analytic continuation from this imaginary, say, time to real time, or this imaginary frequency to real frequency, and this is precisely corresponding to this capital D retarded q omega, which is given by u0 of q times this fully dressed pi, which is this diagram, okay, right here. So in fact, this density correlator in momentum space, but in the zero frequency limit, this corresponds to so-called static structure factor, S of q. So this S of q is defined as 1 over number of particle times this density correlator in Fourier space with this n of q right here and n of minus q on the right. And this correlator is evaluated when q is non-zero, but zero frequency. So that's why we call this static structure factor. So in fact, if you rewrite this correlator in momentum space in the static limit when omega vanishes, then you will find that there's a term when q goes 0, right, which is the delta function, and this gives you only the constant, which is number of charge. But non-zero q component of this correlator is precisely so-called the structure factor. The structure factor is the factor that you could detect or you could observe from the scattering experiment, such as X-ray scattering or electron scattering, and so on. Okay, so this cross-section that comes from your detector in the static limit when omega goes 0 is precisely this capital S of q. Okay, so the capital S of q is directly proportional to the signal intensity that you collect from the scattering detector. Okay, and this is the measurable quantity. Okay, so if you probe the system in the non-zero momentum limit, then this S of q is precisely this density correlation function, okay, in the static limit. Of course, in the more general case, you could consider this SQ omega. This is called a dynamical structure factor. And the dynamical structure factor is, again, like this S of q, is, again, this measurable quantity that you could collect from the detector. Suppose you study this finite momentum transfer between the material, electrons and phonons inside the material, and your, say, electron beam or X-ray beam. And also at the finite frequency. Okay, so if you probe your material by some kind of a scattering experiment, and the intensity of coming from your detector is precisely proportional to this S of q of omega, and S of q omega is the same as this density correlation function. Okay, so this is a very important relation that links what you calculate with what you measured. Okay, in a way that we calculate this 1 over epsilon, this is also what we can measure, because the dielectric function is what we can measure in your lab. Okay, but this is given by this expression right there, and it contains both pure and imaginary components, as we'll see in just a moment. So the both real and imaginary parts of the epsilon, or 1 over epsilon, shows some different meanings, and we will interpret this differently. So at finite temperature, there's a relation between this structure factor and this 1 over epsilon, which is this. Okay, so this comes from this expression at finite temperature. So if you use the spectral representation of this correlation function, and at finite temperature you should be able to derive such a expression right there. So I'll leave this to you as a homework exercise. Okay, you could actually derive this equation from this type of a spectral representation at finite temperature, but this is just some algebra.
Because I want to ask a question. When we talk about the structure factor, I think it's related to the structure of the atom position, right? But if your structure factor is the same as the fundamental solid-state physics,
so this is the structure factor that I'm talking about. Yeah, so you could probe your material right here by some scattering events made of photon beams or electron beams or neutron beams, and then you could put your detector right here to collect this intensity of your scattered X-rays or electron beam or neutron beams, and that you could make a plot of your intensity versus your momentum transfer Q, which is P prime minus P, okay? And also your energy differences between the incoming and outgoing particles, omega 2 minus omega 1. So in general, this is a three-dimensional plot, okay? And you have some intensity profile, and that three-dimensional intensity profile is directly related to this SQ omega.
Because I remember, even for the solid-state physics one, it's for example, you use X-ray, so the profile will relate to the atom's position. My question becomes, your initial Hamiltonian is model Hamiltonian, it's a Gaussian model. So in this case, how we can find the structure?
Well,
because it's uniform positive background.
Well, you could calculate and observe such SQ omega in any kind of solid-state materials, but when you calculate this thing, you could take into account this lattice or without any lattice structure, okay? Either gallium or non-gallium, whatever, okay? So not talking about this any Hamiltonian, okay? So this is independent Hamiltonian, okay? So did I write down any Hamiltonian? No? This is a general relation.
But I think at the beginning you talk about you write Hamiltonian.
Of course, but right here, for any Hamiltonian, I think this relation holds.
Yes, but another thing is if you're not a Gaussian model, the epsilon is a function of capital G prime and the Q omega, right?
I haven't discussed Gaussian model. There's no Gaussian model right here. But here, this is a very general relation between the correlation function, the density correlator, and the structure factor that you detect from your experiments, okay? So you may have different model Hamiltonian, which allows us to calculate this correlator, but we will discuss that later. But independent of what Hamiltonian you have, this relation is there, okay? It's always valid, okay? Which means that whatever the material is, so you can always detect this kind of scattering intensity, right? And this intensity is what you define the structure factor, and the structure factor is related to this correlator, okay? So, but we haven't discussed how to calculate this correlator, but this is, you could say that this is the definition of the structure factor, but the structure factor is directly proportional to the intensity that you collect in experiments, and this could be proof, for example, in your solid state 1, say Oshkov-Mermian or Kittel, in the first few chapters, if you look at these first few chapters of these books, you will have this kind of a relation between the structure factor, and this is the formal definition of the structure factor, theoretically, okay? Independent of what Hamiltonian, whether this lattice is kind of a Jellian approximated or a non-Jellian, okay? So there's always a relation between the structure factor and the correlation function between the density. So now the following question is how to calculate this thing, okay? So what is the Hamiltonian that allows us to calculate this thing, okay? So that's the separate issue. Okay, so the relation that I just wrote here is completely general. It is independent of anything, not anything, but independent of the method that you calculate this density correlator, okay? And this is the way that this experimental signal could be compared with the theoretical calculations. So in the solid state one, you may have such a relation, but you didn't know this relation between the structure factor and this density correlation function. And here, this is the formal definition of a structure factor that you see in your lab. Okay, so this is what I'm trying to say. Okay, good. So let's just look at this density correlation function. This has some peaks, and the peak of this density correlator has some physical interpretations in both the real and imaginary part. So the real part of this capital D of R, suppose we have a peaks of this real part of this density correlator. The position of the peak in the real part of this correlator is the energy of some kind of collective mode. Okay, so the peak position in the real part of the correlator corresponds to the energy of the collective mode, so such as kind of a, say, plasma oscillation in this Coulomb interacting electron gas. So we will come back to this when we talk about this pole or the peaks. But the imaginary part of the correlator also shows some peaks, and the meaningful quantity is the width of the peak corresponds to the lifetime of your quasi-particles. Okay, so we will come back to this when we get there. Okay, so in other words, when we calculate this pi 0, this is what we will do. Just a moment. Okay, so we will evaluate this bubble in the next few steps, and then we get this pi 0 as function of q omega, and we know how to get the pi from pi 0, right? Okay, so once we find this pi 0 and you get pi, when you get the fully dressed electron hole bubble or the polarization, the dressed polarization, you get epsilon or 1 over epsilon. Okay, so this is the way that we compute this dielectric function.
The peak position is the plasma frequency, right? You mean that?
Well, it is the energy of this some collective mode. So you could call this plasma frequency, but we will come back to this when we make some plots of this real part, imaginary part of the epsilon. Okay, so it's not so easy to explain to you this without making the plots. Okay, so we will discuss this, the peak and the width of this real and imaginary part of the epsilon when we get there. Okay, so let's take a short break. When we come back, we start to evaluate this pi 0 and using these Feynman rules. So in this part of calculation, you could refer to our textbook, Flansburgh. There are many detailed calculations, this pi 0, and also the connection to the semi-classical Thomas-Fermi results. Okay, so you could have a look, and later we will see that this purely quantum mechanical treatment of this epsilon in this static and long wavelength limits really corresponds to the Thomas-Fermi results. Okay, so which means that this quantum mechanical treatment does recover this classical or semi-classical theory, but in general at low enough temperature and finite frequency and finite momentum transfer, and this semi-classical theory fails. Okay, only this purely quantum mechanical treatment survives. So there's only one way, which is more accurate way. So this is the only correct way of doing this calculation. Okay, so there's no other shortcut, no other systematic methods for this calculation. So this is the message. As a result, when we finish this 1/epsilon calculation, and you can go back to your introductory level solid state physics, either Oscar Mermion or Kittel's first book, and you can look at all this, the chapter and section in dielectric functions, and you will realize that, oh, this is what we have just calculated, okay? But they simply just summarize the results without further explanation, or only provides the semi-classical treatment. So let's do it by this RPA, or sometimes we call this Linhart, because some part of the results shows a special form of a Linhart function, which is a log correction, logarithmic functions of this energy and momentum. So epsilon q omega is 1 minus u0, pi 0, and pi 0 is this bubble. So let's just write down this finite temperature formulation of pi 0. Okay, so this is a Feynman diagram for pi 0, the single particle hole bubble in Matsubar frequency and momentum space. And you have these two propagators. One is going from the left to the right, another is backwards, which carries different momentum and frequencies. And in particular, we need to sum over this internal degrees of freedom, meaning sum over p and this Matsubar frequency omega n. Remember, this omega n is the fermionic Matsubar frequency, right? Which is what? Which takes the value of the 2n plus 1 times pi over beta, and that we already derived long time ago, right? So this is this fermionic Matsubar frequency, and we need to sum over this Matsubar frequency. So let's just interpret this diagram in terms of this formula. So we need to take this, integrate over this internal momentum p. This is a three-dimensional integration. We need to also sum over this fermionic Matsubar frequency omega n here, and this 1 over beta is just the definition of this Matsubar sum. And there are two propagators, Bayer propagators. One is right here, which is 1 over I omega n minus epsilon p. Another is the bottom propagator right here, which is 1 over I omega n plus I omega. Well, we can rewrite this in terms of the following expression. In other words, we could re-express this product out of these two simple Bayer-Green's functions in terms of this subtractions of this energy denominators and divided by this factor. Good, so this is it. So if you simply just combine these two, okay, and this factor, you could actually show that this is the same as that one. Okay, good. So now the remaining text is really simple, because this factor is independent of this Matsubara sum. Okay, so and we could just perform this Matsubara sum first, which involves just two separate simple poles, right, of this Bayer-Green's function. And following our earlier results, we could immediately write down the final expressions after Matsubara sum. Remember, when we sum over this Matsubara of the simple pole, you could use this contour integration, right? And then you could easily see that this is nothing but this Fermi function. Okay? So remember, this is what this is. Okay, so then this is nothing but its Fermi function. So maybe I could just leave this to you as a homework exercise. And you can easily derive this results from this contour integration. Okay, good. So, and the second term could be evaluated in a similar way. Okay, so where you get what this f0 epsilon p plus q here. And well, of course, there's some little subtlety right here. So when you evaluate this second mass bar sum, which involve this I omega m plus I omega, so you may have this Fermi function epsilon t plus q plus I omega. Okay, you may end up been doing this after this contour integration, but this is the same as this Fermi function, because remember this external line is actually a single wavy line representing this propagator of this photon, right? So it is actually a bosonic propagator, which represents this Coulomb interaction in the second quantized form. And as a result, this omega actually carried bosonic mass-bar frequencies. Okay? So if you evaluate this Fermi function, where this energy factor is actually including this even mass-bar frequency I omega bosons, and this I omega boson, if you exponentiate it, this is beta I omega boson, right? So this is e to the beta I 2 pi n over beta, right? Which is what? E to the 2 pi I times integer, which is precisely 1. As a result, you actually get back to this, the bare Fermi function f0 as a function of the epsilon p plus q. And this minus sign here, you can keep track of this minus sign. Good. So this is just a simplest example of this electron hole bubble that could be evaluated by this contour integration that we already studied. Okay, so but we have one more step to go, which is to sum over this momentum. And this is somewhat messy because it involves this Fermi function, this difference between these two Fermi functions. Also, it involves the energy denominator. So in this denominator, you get this difference between these two bare electron kinetic energy, and you get the three-dimensional integration over p. So this looks really messy. But let's just try to simplify this. So we should talk about these two limits. One is the classical limit when temperature goes to infinity. Another is, the purely quantum mechanical limit when temperature goes to 0. So you will see that this classical limit, this quantity recovers exactly this Thomas-Fermi results. But in this quantum limit, you will get something new, okay, which was not able to get by any classical or semi-classical treatment. But let's just do easy things first. Let's just look at this classical limit. So when temperature goes to infinity, this external frequency, say omega, is actually 2 pi n over beta, is actually beta goes to 0 when temperature goes to infinity, right? Which means that this Matsubara frequency or external Matsubara frequency omega is actually almost, say, either infinity or 0. All right? So, but we don't care about when this omega becomes infinity because you don't get anything meaningful. So you only focus on this 0 frequency limit when omega becomes 0. So we only need to consider omega goes to 0 limits, which means that n goes to 0. Okay, which means that we only care about this static limit when the external frequency is exactly 0. So when that occurs, you could forget about this I omega right here, right? Because omega is either 0 or infinity. So when omega is infinity, you don't get any contributions because 1 over infinity is 0 always. Okay, so in that limit, this static limit is given by this integration. Okay, so let's just look at this high temperature form of this Fermi function. So when temperature goes to infinity, this Fermi function is approximately given by this exponential, right? Because the Fermi function is what, right? Okay. So when beta goes to infinity, which means that this exponential factor is really, really large compared to 1. So you could simply just forget about this constant, okay, from the denominator. And this is it. Okay, so you could simply just use that as the high temperature Fermi function. Well, so let's take a short break. When we come back, we will continue evaluating this high temperature results. Okay, so let's just start to evaluate this integral. So this is the last line before the break. But this pi 0 is given by this in the high temperature limit is given by this moment integration in 3 dimensions, whereas the integrand is given by this difference between these two Fermi functions at different momentum p plus q and p, and divided by this energy denominator. So, but we could show pretty easily that the first term marked by yellow is actually the same as the second term right here. Suppose you simply just shift your integration variables p to actually p minus q. So the p plus q under such a shift is going back to p, and so this energy denominator becomes epsilon p minus q, which is precisely written here, and this is the same as the second term. So overall you got factor of 2, extra factor of 2 here. So this original factor of 2 comes from the spin. Okay, so you get another factor of 2 because these two factors are identical. Great. So then we could perform this moment integration. Okay, so bear in mind that these energies are the spare electron kinetic energy, which is quadratic dispersed, and this, when you subtract this epsilon p from this epsilon p plus q, you get this minus q squared plus 2pq cosine theta divided by 2m. So cosine theta is the angle between p and q. So remember, this p and q are general vectors in 3-dimensional space, so it could point to any direction, so they can have any theta. So in other words, we need to integrate it over this 3-dimensional momentum vector p, but you could do it in terms of this radius part of the integration times this angular part. The angular part is the theta integration. Okay, so let's just define this x as cosine theta. Then we know that you need to integrate it over this theta from, say, 0 to pi, right? And which corresponds to this cosine theta being plus minus 1, right? So let's just rewrite this pi 0 in terms of double integrations. One is the magnitude of the p, another is the cosine theta, which is x. Okay, so you could perform this integration over x first, because this is just, you could check the table integration. So let me just write it down. The result is a log function of p and q, and then you could simplify this using this approximated form of the Fermi function, the high temperature limit, and we define two variables, lambda or lambda squared, which is thermal wavelength, and also we define this spectral function phi as function of q times lambda. Okay, so phi of x is this. It's very complicated integration, but it has some very simple asymptotic behaviors. So this phi of x function, when x is 0, is actually 1. Okay, so you could very easily verify this. But when x is very large, when x is almost infinity, and phi of x decays as 1 over x squared. So let's just look at this correspondence between this high temperature result of a quantum mechanical treatment and the semi-classical Thomas-Fermi result. Okay, so to see this, we need to make a further approximations. Namely, suppose the q is very, very small momentum transfer, or a long wavelength limit. We know that from this de Broglie relation that this q inverse is actually proportional to the wavelength, right, of the quantum matter wave. So when momentum transfer is small, equivalently this wavelength corresponding to this momentum transfer processes is actually very long, which corresponds to low energy excitations, low energy and low momentum transfer excitations. So in that limit, it's pi 0 of q0 is approximately just a constant, because when q is very, very small, which means that q lambda is really small, which means that when x is very small, when x is simply just q times lambda, right? So I just told you that when x is 0, this phi function, phi of x is actually 1. So you simply just plug in this limiting case, then this epsilon RPA in a static and long wavelength limit takes a very simple form, which is the same form as q Thomas-Fermi square, right? Okay, so let's see this. So pi 0 is just constant. How do we see this? Lambda, let's do the algebra. So this is lambda to the power of -3, which is beta, but this is e to the beta mu, and there's a factor of beta, but beta goes to infinity. So we'll look at this later, right? So we check this later. So let's take a short break. When we come back, we will study this quantum limit. Okay, so again, so this form is exactly the same as this Thomas-Fermi, because in the Thomas-Fermi approximation, this is q Thomas-Fermi square, or q square. Okay, so we have studied this Thomas-Fermi approximation the previous semester. So if you look back to your earlier notes, then you'll find this constant QTF, which defines this cutoff your Coulomb interactions, and this is the source of the screening of a Coulomb potential. Okay, so because of this special form with epsilon, so if you look at this U effective, which is the U0 of Q divided by this epsilon of Q. So if epsilon Q is given by this, and you simply just plug that in, and you perform the Fourier transformation back to the real space, and you'll find that this Coulomb potential, the effective Coulomb potential, is actually decay really fast. Okay, so beyond so-called Thomas-Fermi length, there's almost no Coulomb potential. Okay, and this is the source of the screening. So we recover the screening of a Coulomb potential in this high temperature limit. Okay, so let's take a short break. When we come back, we will see these factors and also continue working on this quantum limit. Okay, so let me just make some remark on this classical limit. As we just mentioned, that pi 0 in this limit is actually the constant, which is the minus some positive constant. And this constant is actually a universal constant, but it is a function of temperature, right? So this is a function of beta, e to the beta mu, and so on and so forth. And lambda is also a function of temperature. But the point that this, we call this a constant because it is independent of the momentum q. And so in that regard, this epsilon RPA take this the same form as that we obtained by Thomas-Fermi, but of course this QD is not the same as Q Thomas-Fermi. So this classical limit is in fact not so relevant, and it is unrealistic because we are more interested in this quantum region where temperature goes 0. But it's just a nice kind of a result that you recover the same form as Thomas-Fermi results, but it, of course, this prefactor is not the same. Okay, so let's just look at this quantum region, which is more relevant. Again, so we need to evaluate this nasty formula. To do so, we could take advantage of this complex analysis contour integration. We could consider a general complex variable z, which is generalized from this I omega. Now, omega is the Mozart bar frequency for external photon propagator. So in this more general form, you could try to take advantage of the complex analysis. Yeah, and then you could perform this analytic continuation, say, when z goes to, say, the real frequency, and we could evaluate this, the real part of pi 0 in the real frequency limit. Okay, so then you could just perform this integration over p, and which is further decomposed into this amplitude, radius part of the integration and angle part of the integration. So again, so when we separate this integration over momentum p into the amplitude or radius parts and the angular part shows the factor of the sine theta d theta, and divided by this a constant a plus another constant b times cosine theta, which is what we have here and there. So then this gives us a log, magnitude log. So at 0 temperature, this Fermi function reduces to the moment integration from your lowest value up to the Fermi momentum, right? So the radius part of your integration, starts from the 0 radius to up to the maximum radius, which is your Fermi momentum. Okay? So the Fermi function now becomes the theta function in a sense. So then we could write down the final results. Okay, so let me just write it here. Okay, so let me just write down this final result for this epsilon RPA, the real part, which is given by this complicated messy function of log and some function of the epsilon q plus or minus omega square and those factors. But we could also see that in the static limit or the semi-classical limit, when omega goes to 0, if you simply just make omega 0, and what you get is precisely this Thomas-Fermi factor. Okay, and you can see that in this classical limit or this static limit, when omega goes to 0, and this real part of this epsilon or real part of the dielectric function reduces to precisely this Thomas-Fermi form. So this time, this correspondence is actually real. So this will be your another homework. Prove this, and you could derive this Q Thomas-Fermi and show that it is indeed this Q Thomas-Fermi via this semi-classical method, which means that in this low temperature limit, this quantum treatment, purely quantum mechanical treatment, indeed reproduces this semi-classical Thomas-Fermi result. And here this Q Thomas-Fermi is indeed some constant which is independent of temperature and momentum. It's just a function of what this density of states and Fermi momentum and the mass and so on. Okay, so here in the middle, I just summarize how we derive, how we get to this messy function of log. So by computing this principal value of this integral, remember this is what we just derived previously, that this electron hole bubble in its quantum limits can lead to such an integration over the magnitude of momentum and the angular part of the integration over d cosine theta. And once you evaluate this dx, and you get this complicated log functions, which I call this f of y and y0, and this y is simply the dimensionless variable q divided by 2kf, and y0 is again dimensionless variable omega divided by 4 times Fermi energy. And the whole thing, the real part of pi 0 is simply just a density of states at Fermi level times this complicated factor 1/2 plus this f function. Okay, but you could use this relation between this epsilon and pi 0. Remember that. Okay, use this relation. So once you found this pi 0, and plug in here and take the real part, and that's it. Okay, so that's what you have after going through all this messy integrations over internal momentum. Okay, so these log functions sometimes we call the Linhart function, and this Linhart function, this log magnitude of a log function, log of the magnitude of this complicated function, so appears in many solid state textbooks in Kittel's Alcott-Mermion. Great. So we're just halfway through the full calculation. So we just finished this real part of the epsilon. So next we will try to evaluate this imaginary part of that, epsilon. Okay, and then we could make some plots of this so-called this kind of a three-dimensional plots of epsilon versus q and omega, and we'll see a new physics emergence from this calculation, namely this plasma oscillation and also Landau damping physics. Okay, so that is the subject for this next lectures on Thursday. Okay, so that's enough for today. Okay.
Yeah. Excuse me. For the imaginary part, you want to use the Kramer-Poisson relation, or we cannot use it because they're Q dependent.
This is a good question. So as you'll see next time, so we don't simply just use KK relation. We directly compute the imaginary part. Okay, by this Cauchy principle, you know that. Okay, so once we have this Green's function and we take the imaginary part, and this, remember this, what imaginary part is what I pi the principal value of 1 over x, right? So we simply just use that.
Principal value over minus plus I pi.
Delta function, right? It's a delta. Anyway, so we simply just use Cauchy principal theorem, the value of the imaginary part. Okay? Yeah, this is a good question. So you may prove that the real and imaginary part satisfies the KK relation. I didn't check that, but you could check this. They should satisfy the KK relation. But this real part is complicated enough, so once you use KK relation, so...
I think numerical is possible.
But the thing is that we could achieve some analytical expression. Why bother using numerics? Okay, so that's my point. If we could solve this exactly, we could check by numerics, but we don't have to. Okay, great. So I'll see you on Thursday.